Good morning, students. In previous class we have seen variation of atomic radius in d block elements. It is not continuously decreasing up to the zinc. Even we have seen that exactly how it is going to be happen by using a curve. Okay, in today's class we will start with the variation of ionization energies in d block elements. First, to understand this ionization energies, variation of ionization energies in d block elements, we want to know the definition of ionization energy. Okay, to understand the definition of ionization energy, let us consider one metal. This is in solid state. Okay, now a metal M in solid state should be converted to, should be means it is going to involve in chemical reactions. While it is undergoing chemical reactions, it is going to be converted to M plus 2 or M plus 1. Okay, or M plus 3, whatever it is. For example, here I am telling it is M plus 2. Okay, so a metal in solid state is going to be converted to M plus 2 in gaseous state involves the following steps. What are they? Steps are nothing but what are the different forms of energies involved in this conversion. Metal solid is converted to M plus 2 gas. Okay, first metal solid should be converted to metal gas, that is by using the energy delta HA, which is called heat of atomization. What is that? Heat of atomization. Metal solid by absorption of energy, enthalpy of atomization or heat of atomization, which is represented by delta HA. It will be converted to metal atoms. This is in atomic state gas. Now this one should be converted to M plus unipositive ion in gaseous state by the absorption of some energy, which is called ionization energy 1. After completion of this, I will tell the definition also, which is called ionization energy 1. Now this metal plus unipositive ion is converted to M plus 2 gaseous state, okay, by the absorption of some more amount of energy, which is called ionization energy 2. Which is called ionization energy 2. Is it okay? Now see, M solid is converted to M plus 2 gas by the following energy changes. What are they? Heat of atomization, ionization energy 1, ionization energy 2. These many things are there. Delta HA, delta H1. Delta H1 is called ionization energy 1. Delta H2 is called ionization energy 2. All these total amount of energy will be absorbed to convert this metal solid state to metal plus 2 gas. Is it clear? Now I hope you understood what is meant by ionization energy. The meaning of ionization energy: the amount of energy required to remove the electron from neutral isolated gaseous atom. The amount of energy required to remove the electron from neutral isolated gaseous atom is called ionization energy. If it is from neutral isolated gaseous atom, that is called first ionization energy. If it is from unipositive ion, that is called second ionization energy. If it is from dipositive ion, that is called third ionization energy. Like that, by the absorption of first ionization energy, neutral atom is converted to M plus, unipositive ion. By the absorption of second ionization energy, M plus is converted to M plus 2. By the absorption of ionization energy 3, M plus 2 will be converted to M plus 3. Like that, keep on going on according to the stability of the atoms and ions. Okay, now the main point here is factors that affect ionization energy. Factors affecting ionization energy. What are the factors? Those are going to affect the ionization energy. First one, atomic size. Second one, shielding or screening effect. Third one, electronic configuration. Here itself I am telling that D3, D5, D10 are stable configurations under D subshell. To remove the electron from these configurations, it requires very high amount of energy. Is it okay? To remove the electron from these configurations. That means D3, if you want to remove the electron to become D2, high amount of energy is required. From D5, if you want to remove the electron, same like that. D10 also like that, because these are stable configurations for D subshell. What is this D3? Coming to coordination compounds, this D subshell, D orbitals are divided into two categories, T2G and EG. T2G contains 3 orbitals, EG contains 2 orbitals. Okay, now D3 is nothing but half-filled T2G. What is that? D3 is nothing but half-filled T2G. That's why it is stable. But D6 will not come under completely filled T2G, because 2 electrons will enter here and 1 electron is coming here. That's why D6 configuration is not included in stable configuration. D6 configuration is not involved in stable configuration, but D3 configuration is involved because T2G set is getting half filled. Is it okay, ma? As it is half filled T2G set, it is more stable. D5 totally half filled stable configuration, half filled configuration. D10 completely filled configuration. This is half filled T2G. This is fully D subshell half filled. This is fully filled D subshell. Those are very stable configurations. It requires very high amount of energy to remove the electron from these configurations. Is it okay? Next, atomic size, shielding or screening effect, electronic configuration. These are the factors they are going to affect the ionization energy. Okay, in this, depending on any one factor, we can say why that atom has high ionization energy or low ionization energy, like that we can say. For example, one example I will tell, which is not related to D block. Let us consider nitrogen and oxygen. Actually, left to right, what happened? Atomic size decreases. Nitrogen is bigger than oxygen. Nitrogen is bigger than oxygen. When nitrogen is bigger than oxygen, ionization energy of nitrogen must be less than ionization energy of oxygen. Because this is bigger nitrogen, easily we can remove the electron. Nitrogen is bigger than oxygen, correct? We can remove the electron. Like that we are thinking according to atomic size. According to atomic size, we are thinking that nitrogen, from nitrogen we can remove the electron easily. That's why ionization energy of nitrogen must be less than ionization energy of oxygen. But practical value is showing that ionization energy of nitrogen is greater than ionization energy of oxygen. So this factor, which is this rule, which is explained by electronic configuration, not atomic size. Depending on atomic size, here if you explain, it is wrong. So which is playing important role, or which factor is dominating others? Here electronic configuration. Okay, nitrogen electronic configuration is 1s2 2s2 2p3. Oxygen electronic configuration is 1s2 2s2 2p4. Removing of electron from 2p3 is very difficult because it got half-filled configuration. Here it is not half-filled, so we can remove the electron easily. That's why ionization energy of nitrogen is greater than ionization energy of oxygen. Even nitrogen atomic size is greater than oxygen. Even nitrogen atomic size is greater than oxygen. Depending on electronic configuration, ionization energy of nitrogen is greater than oxygen. Is it right? Depending on this, like this, we can compare with copper and zinc also. Now let us concentrate on copper and zinc. See, copper and zinc. What is the ionization energy of zinc? 906. What is the ionization energy of copper? 745. According to our graph, zinc is bigger than, atomic size of zinc is, copper is smaller than zinc. Then we are thinking that copper has higher ionization energy than zinc, but practical values, ionization energy of copper is smaller than ionization energy of zinc. This is explained depending on electronic configuration. I think now you are getting the point. That's why here, after completion of the class, I will take the pick of this total analysis. Depending on which factor, this copper and zinc ionization energies are like this. If you depend on atomic size, we cannot explain this one because zinc is bigger than copper. So zinc should contain less ionization energy than copper. But here zinc contains high ionization energy than copper because zinc has highly stable configuration 4s2 3d10. From that, if you want to remove the electron, this is completely filled, this is also completely filled. If you want to remove electron, it requires high amount of energy. But copper 4s1 3d10, 4s1 is half filled, okay, but this half filled configuration is less stable than full filled configuration. So we can remove the electron from copper somewhat easily when compared to zinc. That's why zinc ionization energy is 906 kilojoules per mole. Then copper ionization energy is 745. Now I think you got the point of this one. Is it okay? So everything, unipositive ion, dipositive ion, everything I analyzed this one and I wrote on this paper, and depending on which factor we are going to explain the variation in ionization energy, I wrote clearly. Everything I have written here neatly. They gave only tabular column. This one fully I will take one pic and I will send to you. There is not a problem here. But you have to understand what is happening here. See, here shielding effect is playing important role. Here electronic configuration is playing important role. Size, atomic size, electronic configuration. EC means electronic configuration. So immediately, if you see electronic configuration, this is EC, screening effect or shielding effect, atomic size. Depending on these factors, we are going to explain the ionization energies of D block elements, how they are going to be varied. Okay. Now clearly you got the point, I think. Even nitrogen is bigger than oxygen. Ionization energy of nitrogen is greater than ionization energy of oxygen. That is depending on electronic configuration. Like even zinc size is greater than copper. Zinc ionization energy is greater than ionization energy of copper because depending on electronic configuration. Zinc stable configuration is 4s2 3d10. It is highly difficult to remove the electron from stable configuration. That's why zinc has higher ionization energy than copper. Like that, depending on various factors, okay, why that atomic sizes are varied like that. These many things why we have to consider in d block elements, because there is no regular trend. In ionization energy values, there is no regular trend in ionization energy values for d block elements. So somewhere it will increase, somewhere it will decrease, again it will increase and it will decrease. Like that, one regular trend is not there. Regular trend means whether it will increase or decrease from left to right. Like that, one regular trend is not there. There is no regular trend in ionization energy values for d block elements. That's why we want to see everything reason, and we want to understand how that reason is going to explain the ionization energy values of d block elements. That is one we are going to see now. Are you okay, ma, till now? So if a neutral atom is going to be converted from solid state to M+2 gas, these many energies are required. This delta HA is called enthalpy of atomization. This is called first ionization energy, and this is called second ionization energy. Like that, I gave introduction about ionization energy, factors affecting ionization energy, and depending on factors, how we are going to explain the ionization energy values of d block elements also we have seen. Okay, now let us see now what about the analysis of this one. I hope you are clear only, ma. See now, scandium to titanium. Scandium atomic ionization energy 631, titanium 656. There is a increase in ionization energy, that is size decreases. Scandium is bigger than titanium, that means titanium is smaller than scandium. It has higher ionization energy than scandium. So here size is enough to explain the ionization energy value. Here titanium to vanadium, 656 to 650 decreased. Slightly it is decreased because 4s to 3d2. Configuration of titanium is 4s to 3d2. Vanadium 4s to 3d3. Okay, ma? Here which is playing important role? Electronic configuration is playing important role. Here completely 4s1 3d3 we are getting V plus. V is converted to V plus 4s1 3d3 simply by removing one electron from 4s. Just 1 second, ma. Here instead of electronic configuration we can write shielding effect. Sorry. Electronic configuration only. Electronic configuration only. Vanadium 4s2 3d3 will become 4s1 3d3 by losing one electron. That's why it will lose the electron easily. That's why IE1 of vanadium is less than IE1 of titanium. Okay, next, vanadium to chromium. What happened to ionization energy? Increased. Here size only it is going to explain the factor. Size is the factor which is going to explain. Vanadium to chromium size decreases, ionization energy increases. Chromium to manganese also size only. Chromium to manganese size decreases. That's why ionization energy increases. Okay, manganese to iron also size only. 717 to 762. So when there is size factor, easily we can understand. Now coming from iron to cobalt. Actually iron to cobalt very slight decrease in size only. 760 to 758. 760 to 758. See, there is a decrease in ionization energy. That is because of shielding effect. Here shielding effect is playing important role. When shielding effect is increased, outermost electrons are not under the influence of nucleus. When shielding effect is increased, outermost electrons are not under the influence of nucleus. we can remove the electron easily from 4s. That's why from iron to cobalt, what happened to ionization energy? Decreases. When shielding effect is increased, nucleus cannot hold the outermost electrons effectively. So we can remove the electron easily. Here, size is not the matter. Shielding effect is going to explain from 762 to 758. Next, cobalt to nickel also, shielding effect is increased. We can remove the outermost electron easily. So 758 became 736. But from nickel to copper, even copper is bigger than nickel. Electronic configuration will play the important role here, as copper got stable 4s1 3d10, half filled, full filled. Half filled, full filled. Stable configuration 736, here copper 745. Even copper is bigger than nickel. Next, zinc. From copper to zinc also electronic configuration plays the important role, because zinc is bigger than copper. Till previously also I explained 4s to 3d10 is stable configuration. Energy required to remove the electron from stable configuration is difficult. That's why high amount of energy is required. Okay, like this. Sc plus 1, 2, 3, 5. Every time IE1 is greater than IE2 is greater than IE1. Every time IE2 is greater than IE1. For every atom, definitely IE2 is greater than IE1, because energy required to remove the electron from neutral atom. This is energy required to remove the electron from unipositive ion. From unipositive ion, it is slightly difficult when compared to from neutral atom. Nuclear charge is high, so energy required is high. Sc plus 1, 2, 3, 5. Ti plus 1, 3, 0, 9. Here also size increase only. Titanium plus 2 V plus. Here also size only 1, 4, 1, 4. So when there is a increase in ionization energy, simply we can write size factor. Ti plus is greater than V plus. V plus is greater than Cr plus. So again there is an increase in second ionization energy. These are all second ionization energy values Cr plus 1592 to 1509. Here electronic configuration is playing important role. Mn plus has 4s1 3d5. Cr plus has 4s0 3d5. We have to remove electron from 3d5. Here we have to remove electron from 4s1. 3d5 is more stable than 4s1. That too, this is present in third shell. Highly attracted by nucleus. So it has high ionization energy when compared to Mn plus. What is meant by IE2? 1509 amount of energy is required to remove the electron from 4s1. 1592 is the amount of energy required to remove electron from 3d5, because 4s0 here. So energy required to remove the electron from 3d5 is greater than energy required to remove the electron from 4s1. So here electronic configuration is playing important role. Next, Fe plus CO plus, increase in ionization energy, size factor. CO plus is smaller than Fe plus. Now CO plus to Ni plus also, Ni plus is smaller than CO plus, increase in ionization energy only. Here also size is explaining. But coming to Ni plus to CO plus is greater than Ni plus. Again we are seeing that electronic configuration plays the important role. What is the electronic configuration of Cu plus? 4s0 3d10. Energy required to remove the electron from 3d10 is very high. That's why 1958 amount of energy is required to remove the electron from 3d10. From Cu plus to Zn plus, again electronic configuration 1734. But here see 1958 and 1734, there is a decrease in value, because Here energy required to remove the electron from 3d10, third shell. Here energy required to remove the electron from 4s1, fourth shell. This energy is less when compared to 3d10. Even configuration wise, if you see, this is less stable when compared to 3. Actually, 3d10 is more stable when compared to 4s1. This is completely filled, this is half filled only. That's why this electron can be removed easily when compared to electron from 3d10. That's why 1958 here 1734. I hope everyone you are understanding, ma. Everything I wrote neatly, the reasons also. Simply by observing these reasons, you can understand easily. Okay, and we can analyze the things also easily. But no need to remember these values. These are all given in textbook and I noted down. Reasons are very important. That is the main thing here. Okay, same like this. Coming to third ionization energy values. Third ionization energy value must be greater than second ionization energy value. Every time IE3 is greater than IE2. Okay, scandium plus 2 to Ti plus 2 size, Ti plus 2 to V plus 2 size, V plus 2 to Cr plus 2 size, again increase only. Increase means there is a decrease in size. From Cr plus 2 to Mn plus 2 also size only. But Mn plus 2 to Fe plus 2 electronic configuration. See 3260 2962. Here electron must be removed from 3d5 half filled configuration. Here electron must be removed from 3d6. This is not half filled or full filled. Easily we can remove the electron from Fe plus 2 when compared to Mn plus 2. That's why here high amount of energy is required. This is third ionization energy of Mn plus 2 is greater than third ionization energy of Fe plus 2, which is explained by electronic configuration. From Fe plus 2 to CO plus 2, again size. CO plus 2 is smaller than Fe plus 2. That's why it has higher ionization energy. CO plus 2, Ni plus 2, again size factor 3402. Ni plus 2 is smaller than CO plus 2. Next, Ni plus 2 to Cu plus 2. Here hydration enthalpy. Cu plus 2 has higher hydration enthalpy in aqueous solution. Because of that, it is highly stable. Hydration energy, I will explain the definition separately. It has higher hydration energy in aqueous solution. Maximum these ions are present in aqueous solution only. Cu plus 2 has higher hydration energy, so it is more stable in water. That's why it is very difficult to remove electron from Cu plus 2. It requires very high amount of energy, 3556, when compared to Ni plus 2. This is explained depending on hydration energy. Coming to again Zn plus 2 electronic configuration, because it got 3d10, 4s0 3d10. Energy required to remove the electron from 3d10 is very high. Even it is dominating the aqueous solution stability of Cu plus 2 also. That's why 3829 is the ionization energy of Zn plus 2, which is not at all possible to supply for Cu plus 2 and Zn plus 2. So there is no chance of Cu plus 3 and Zn plus 3. This is 3556, this is 3829. Very high amount of ionization energies are required to convert Zn plus 2 to Zn plus 3, as well as Cu plus 2 to Cu plus 3. That's why Cu plus 2 is the more stable cation for copper. Zn plus 2 is the most stable cation for zinc. Up to that only. Zn plus 3 is not existed. Cu plus 3 is also not existed, because to convert Cu plus 2 to Cu plus 3, very high amount of ionization energy is required. To convert Zn plus 2 to Zn plus 3 also, very high amount of ionization energy is required, which is not at all possible for us to supply. Okay, I think this total analysis definitely it will help you to understand ionization energy values. Okay, this one separately I will take the pick in cam scanner and I will send to you in our group. Before that, I hope everyone is understanding. And what about the definition of ionization energy and what are the factors affecting ionization energy, everything clearly it was explained. Now we will read the textbook points whatever they have given in under ionization energy. Everything till now, what are the explanations I gave, they were given in this parapolymer. Just I will read and I will go through next concept. Due to an increase in nuclear charge which accompanies the filling of the inner d orbitals, there is an increase in ionization enthalpy along each series of the transition elements from left to right. However, many small variations occur. There is only no regular trend happened here. Table 8.2 gives the values for the first three ionization enthalpies of the first row elements. See, this is the tabular column which was given in your textbook. By using this tabular column values only, I have explained till now. But by writing like this, slightly confusion will be happened. So I wrote neatly along with every element and I explained till now. These are the values only I mentioned. Okay, ma? First row element. These values show that the successive enthalpies of these elements do not increase as steeply. Steeply means continuously, as in the main group elements. Although the first ionization enthalpy in general increases, the magnitude of the increase in the second and third ionization enthalpies for the successive elements in general is much higher. These are all normally known things only. Second and third ionization energies will be greater than first ionization energy automatically. Okay. The irregular trend in the first ionization energy enthalpy of the 3D metals, though of little chemical significance, can be accounted for by considering that the removal of one electron alters the relative energies of 4s and 3d orbitals. So the unipositive ions have dn configurations with no 4s electron. There is thus a reorganization energy accompanying ionization energy with some gains in exchange energy as the number of electrons increases and from the transference of s electrons into d orbitals. Okay, there is the generally expected increasing trend in the values as the effective nuclear charge increases. However, the trend in the values the value of chromium is lower because of the absence of any change in the d configuration, and the value of zinc higher because it represents the ionization energy from the 4s level. That one only. Till now, electronic configurations, shielding effect, atomic size, those are the factors which affect. In terms of small points like that, they gave here. The lowest common oxidation state of ionization these metals is +2. To form the M+2 ions from the gaseous atoms, the sum of the first and second ionization enthalpies is required in addition to the enthalpy of atomization also. See, what are the energies required? First and second ionization energies in addition to the enthalpy of atomization for each element. The dominant term is the second ionization enthalpy, which shows unusually high values for chromium and copper because of electronic configuration. D5 and D10 configurations of the M+ ions are disrupted. With considerable loss of exchange energy, the value for zinc is considerably low as the ionization consists of the removal of an electron, which allows the production of the stable D10 configuration. The trend in the third ionization enthalpies is not complicated by the 4s orbital factor and shows the greater difficulty of removing an electron from the D5 and D10. It is very difficult to remove the electron from D5 and D10 configurations ions superimposed upon the general increasing trend. In general, the third ionization enthalpies are quite high and there is a marked break between the values of Mn+2 and Fe+2. Everything it was explained. Once go through again. Okay. Also the high values for copper, nickel and zinc indicates why it is difficult to obtain oxidation state greater than 2 for these elements. Already explained, ma. That is the explanation. Third ionization enthalpies are very much higher. Okay. Although ionization enthalpies give some guidance concerning the relative stabilities of oxidation states, this problem is very complex. Anyways, to study this one, it is slightly difficult only, but we try to explain everything clearly, okay, and not amenable to ready generalization. Generalization is not possible. That's why individual atoms we considered and we explained. That is the thing we got from here. Okay, ma'am. Now, next condition is oxidation states we will see. Before going to that one, oxidation states, till now we have gone through ionization enthalpy values, how they are varied in D block elements. I hope you are clear, everyone. Okay, next side heading is oxidation states. One of the notable features of a transition element is the Great variety of oxidation states it may show in its compounds. Table 8.3 lists the common oxidation states of the first row transition elements. Scandium to zinc, general oxidation numbers are shown. The most common ones are in bold types. Example, iron will show more in +2 and +3. In bold letters they gave +4 and +6. Very rarely it will show. Okay, ma? Now see. Here also one important thing we can remember easily. Left to right, scandium to manganese, number of unpaired electrons are increased. When number of unpaired electrons are increased, number of variable oxidation states also increase. For example, scandium has 1 unpaired electron, titanium has 2 unpaired electrons, vanadium has 3 unpaired electrons. If you write the configuration, you will understand. Scandium has 1 unpaired electron, titanium has 2 unpaired electrons, vanadium has 3 unpaired electrons, chromium has 4 unpaired electrons, chromium has 5 unpaired electrons with 4s1. Manganese has 5 unpaired electrons. Iron has 4 unpaired electrons. Cobalt 3. Like that, up to manganese, number of unpaired electrons are increased. So, manganese can show more number of oxidation states. Even chromium also will show more number of oxidation states. Even manganese also will show more number of oxidation states. Again, number of unpaired electrons are decreased. So, number of oxidation states they can show, that is also decreased. See, scandium will show only 1 oxidation state +3. Titanium can show +2, +3, +4, but the most oxidation state is +4. See, they can use 4s2 electrons. 4s2 electrons, 3d1 electron, +3. 4s2, 3d2. All the electrons if they use, it will show +4. Are you getting my point, ma? By using 2 electrons, 4s2 electrons, by losing that 4s2, it will get +2. By losing 4s2 3d1, means 3d2 electrons are there in that 1 electron, and 4s2 electrons, it will show +3. By losing all the electrons, it will show +4. Like that, vanadium, furthermore chances are increased. When number of unpaired electrons are increased, chances of showing more variable oxidation states are also increased. So vanadium can show +2, +3, +4, +5, but in +5 more rapidly it will be happened. It will be occurred in highly +5 oxidation state. Chromium +2, +3, +4, +5, +6, but majorly it is occurred in +3, +6. Manganese +2, +7 highly, but it can show +2, +3, +4, +5, +6, +7. Like that, we can remember easily when number of unpaired electrons are increased, there is a chance of that element to show higher oxidation states also. More number of oxidation states. See, now they gave the explanation. The elements which give the greatest number of oxidation states occur in or near the middle of the series. Manganese, for example, exhibits all the oxidation states from +2 to +7. The lesser number of oxidation states at the extreme ends stems from either too few electrons to lose or share, scandium, titanium, or too many d electrons. Hence, fewer orbitals available in which to share electrons with others. Very fewer orbitals are there, very less number of orbitals are there to share with others. For zinc, 4s2 3d10. 3d10 electrons, they won't participate in reaction. It will be involved in 4s2 only. That's why it can show only +2 configuration, +2 oxidation state. For higher valence available in which to share electrons, for higher valence copper, zinc. Thus, early in the series, scandium is virtually unknown. Scandium 2 is virtually unknown. See. And titanium 4 is more stable than titanium 3 or titanium 2. At the other end, the only oxidation state of zinc is +2. No d electrons are involved. The maximum oxidation states of reasonable stability corresponding value to the sum of s and d electrons up to manganese also. Titanium 4 O2, vanadium 5 O2 plus, Cr6 O4 minus 2, Mn7 O4 minus, followed by a rather abrupt decrease in stability of higher oxidation states. So that typical species to follow are Fe 2, 3, stable, iron is stable in 2, 3 oxidation states, cobalt is stable in 2, 3, nickel 2, copper 1, 2, zinc 2. These are the general oxidation numbers of various elements. The variability of oxidation states, a characteristic of transition elements, arises out of incompletely filling of d orbitals in such a way that their oxidation states differ from each other by unity. Example, vanadium 2 unity differentiated by unity next to V3, V4, V5. This is in contrast with the variability of oxidation states of non-transition elements, where oxidation states normally differ by a unit of 2. Unit of 2 meaning non-transition element sulfur. For example, sulfur will show 2, 4, 6, 6, 2, 4, 6. They are differentiated by number 2. But here they are differentiated by 1 because unpaired electrons are present here. So no need to transit the electron. Directly that unpaired electrons only involve in bond. Okay? But non-transition elements like S and P block elements, very less number of unpaired electrons are there. To be unpaired, transition will be taken place and leading to differentiation of 2 Okay? An interesting feature in the variability of oxidation states of the D block elements is noticed among the groups, group 4 through 10. Although in the P block, the lower oxidation states are favored by the heavier members due to inert pair effect. Already so many types we have discussed. The opposite is true in the groups of D block. So we can understand that opposite to that is more stable means nothing but manganese. If you see, lower members of D block elements are more stable in higher oxidation numbers. Generally P block elements, lower members are stable in lower oxidation states, but here lower members are stable in higher oxidation states. That is the meaning, oppositely. The opposite is true in the groups of D block. For example, in group 6, molybdenum 6 and tungsten 6 are found to be more stable than Cr4 and Cr6. Cr6 are found to be more stable than Cr. Chromium is the first element. Molybdenum and tungsten are the lower elements. Those lower elements are stable in higher oxidation numbers when compared to chromium. This is not happened in P block. In P block, top to bottom, lower oxidation number stability increases when compared to higher oxidation number stability because of inert pair effect. Okay. In the Cr6 in the form of dichromate in a acidic medium is a strong oxidizing agent, whereas MoO3 and WO3 are not. So they will not participate in the reactions because they are stable, the MO plus 6 and W plus 6. But Cr plus 6 is highly reactive, that's why it is acting like a strong oxidizing agent. Cr plus 6 is less stable than MO plus 6 and W plus 6. That is the meaning. Okay. Low oxidation states are found when a complex compound has ligand scaffold of pi acceptor character in addition to the sigma bonding. For example, NiCO4 and FeCO5, the oxidation state of nickel and iron is 0. In carbonyl compounds, iron oxidation state, metal oxidation state will be 0. In carbonyl compounds, carbonyls means metal carbonyls. In metal carbonyls, oxidation state of metal is 0. Remember that one. However CO groups are there, oxidation number of metal will be 0. Okay. In metal carbonyls, oxidation state of metal is 0. This is the detailed explanation of oxidation state. In P block elements, top to bottom, lower oxidation state stability increases, but higher oxidation stability decreases because of inert pair effect. But in D block elements, top to bottom, higher oxidation state stability increases. That's why molybdenum and tungsten are stable in 6 oxidation state, but chromium belongs to same group, higher, that means starting member is not stable in 6 oxidation state. That's why it is acting like a good oxidizing agent in aqueous solution when compared to molybdenum plus 6 and tungsten plus 6. These are more stable because lower members are highly stable in higher oxidation numbers. Okay ma? This is the introduction part of oxidation states. I think already I told to you. Now once again I am telling to you, that is 8.3.5 is also there. 8.3.6 small things only, but deep explanation is required. 8.3.7, 8.3.8, 8.3.9, continuation. Everything these are present now. Initially I thought that these values, electrode potential values, friends, in the M plus 2 M standard electrode potential values are not there, but this is also the part of oxidation numbers only. That's why what are the things so far we have covered and what are the things we have to go through, we will have a small glance now. See, 8.1 it is completed, 2, 8.3 is also completed, 3.1, 3.2, 3.3 is also completed, 8.3.4 also it is completed till now. By this class up to 8.3.4 we have completed. Next we have 8.3.5, 8.3.6, 8.3.7, 3.8, like this continuation. Please make a note, ma, small correction is there. These are the things which are present for you. These explanations we will complete in one class up to 8.3.8, 3.5 to 3.8. It will take one class. 3.9, 3.10, 3.12 up to this one class. Remaining 13, 14, 1, 2, 3. These things will be completed in one class. So hardly we require 3 more classes to complete this portion. Okay ma? This is the conclusion for you. I hope you understood the today's class. Thank you all. Have a nice day.